Okay, welcome back. So we have some definitions of extensive form games in hand, and so now we can begin to analyze them. And in particular, let's start out by looking at Nash equilibrium. So our first topic will be Nash equilibrium. After that, we'll find that in the extensive form where there's timing, there will be other ways that we might think of solving a game beyond just looking for equilibrium points in the sense of Nash. So we'll then talk about solving games backwards, and ultimately we'll talk about subgame perfect equilibrium, which is a refinement of, it picks a subset of Nash equilibria. So to begin with, let's start with Nash. And here, again, the definition is unchanged from what we looked at before. So we're going to specify strategies for every player, and we want those strategies to be best responses to what the strategies of the other players are. So each player just has to be maximizing their utility, anticipating the strategies of the others. So it's exactly the same definition conceptually as we had before. The only difference is instead of looking at normal form strategies, now we're working with behavioral strategies in the extensive form. Okay, so to begin to get a feeling for this, let's start by analyzing a Centipede game and trying to understand what Nash equilibrium would predict in this game. So a Centipede game is a very interesting game. It's been studied quite extensively, and it's a game that has a very simple structure. So the extensive form is pictured here. And what happens is we start with player one. So player one is the first mover. They move at the first node, and they have a choice to either stop or to pass to player two. Similarly, then player two has a choice of either stopping or passing, and so forth. And that goes, if they pass, if player two passes, it goes back to player one. They can either stop the game or pass. So at any time the game is stopped, payoffs are realized. Otherwise, the players keep passing on to the other player, and the other player then makes a choice of either stopping or passing. Now, the interesting part about the Centipede game is the structure of the payoffs. So in particular, when we look at the total payoffs here we have a total of 5, here we have a total of 10, here we have a total of 20, here we have a total of 40, 80, 160, 320. So what's happening in this game is as players keep passing, the payoffs are doubled every time. So in terms of getting higher payoffs, if the players can manage to pass a bunch of times, they can end up with much higher payoffs here. So for instance, if they ended the game at the beginning, they get 4 and 1. If they keep moving, they get 256 and 64. So in this case, the blue payoff is the first player, the red payoff is the second player in each one of these entries. So what makes the Centipede game interesting is the fact that although the total sum of the payoffs keeps going up, the size of the pie keeps growing, when we stop at any point in time, the player who chose to stop gets most of the pie. So they get 4/5 of the payoff, and the other player gets 1/5 of the payoff. So if we go back to the extensive form here, what do we see? We see, although we're getting 5, the player who stopped, player 1, is getting most of the payoff. Here, if we stop, it's player 2 who chose to stop. They're getting most of the payoff. Here, player 1 is choosing to stop. They're getting most of the payoff. So the payoff keeps alternating in terms of who gets the most, and the player who chooses to stop is getting a higher amount. And in particular, when we look at the payoffs, so if player 2, for instance, stops here, they get a higher payoff than if they pass it along and then player 1 chooses to stop. So although the payoffs are growing overall, there's an incentive to be the player who stops the game, because the player who stops the game is getting most of the pie at that point. So let's begin to look at what Nash equilibria in this game look like. So in particular, let's look for a pure strategy Nash equilibrium of this game. What do the pure strategy Nash equilibria look like? Well, let's start by just trying to figure out whether it would be possible to get the highest possible payoff. So is it feasible for the agents to just keep passing all the way to get to the highest payoff, which is the total of 320 if they continue to pass all the way across the game. So if we look at this, is this a Nash equilibrium for each player to pass at every single node? Okay, so is this Nash? A Nash equilibrium. Okay, so how do we begin to analyze that? Well, let's take a look at what would happen. Is this a best response? So if we're passing all the way along, then let's just look at player 2's strategy. So they anticipate that player 1's passing all along, they pass all along. Would it be part of a best response for them to pass at the last move? Well, let's look at their payoffs. They get 64 if they pass, 128 if they stop. So clearly 128 is bigger than 64, so they should not pass if they got to the last turn. Instead, they should stop. Okay? So that tells us that all pass is not a Nash equilibrium. Okay, so all pass is not a Nash equilibrium because the second player should deviate from that. They should instead stop the game. Okay, so we can ask that. Well, the first thing we tried wasn't a pure strategy Nash equilibrium. What about passing all the way and stopping? Is that going to be a Nash equilibrium? So we can go ahead and look at that. So here we found that player 2 wants to stop, so now we try all pass all the way along and then stopping for player 2. Okay, does that work? Well, let's have a look. So if we're thinking now that player 2 is stopping here, should player 1 go ahead and pass if these are the strategies that are specified? Well, if they pass along, since player 2 is stopping, they're going to get, player 1's going to get 32. If they stop instead, they get 64. So they shouldn't pass if these were the specified strategies. Instead, they should change their mind and instead stop. So that's no longer a Nash equilibrium. So we can continue in this way. Is it an equilibrium for all players to pass until the second to last move and then to stop? And as we keep going in analyzing this, if we thought that this player was going to stop here, would it be an equilibrium for them to pass along this far? No. For exactly the same reasoning, here player 2 would be facing 16 if they pass. If instead they decide to stop, they get 32. Therefore, they shouldn't pass. They should stop. So as we go through this reasoning, we keep ruling out all these things as Nash equilibria. So when we go through, if we continue to analyze it, it'll continue to break down all the way back to the beginning. And when we find, when we're looking for a pure strategy Nash equilibrium, what are we going to find? If you expect to stop at some node, then whoever was making a move before that should stop at the previous node, right? So the reasoning that we went through just carries all the way back in the game, and the only possible Nash equilibrium outcome involves stopping at the first node. So in this game, if we look for a pure strategy Nash equilibrium, the only possible situation is to have, the only possible outcome is that we stop at the first node. So indeed, there is at least one pure strategy Nash equilibrium. Play stop at every node is a Nash equilibrium. So if everybody anticipates that everybody is going to stop whenever they get a chance to move, so we specify that everyone stops, and then we look at the relevant payoffs. So if it moved all the way along, would player 2 want to stop here? Yes, they get 128 here versus 64, that's better. Would player 1 want to stop at this point? Yes, they get 64 instead of the 32 and so forth. We go back. This is a Nash equilibrium. And in particular, player 1 stopping here is a best response because they anticipate that player 2 is going to stop if they get to move at the second point. Player 2's stopping at this point is a best response. Actually, they never get to move, so it doesn't really matter what they do in the specification of a Nash equilibrium. So in particular, in terms of their best response, so stopping is a best response given that player 1 stops at the first move. So if we're looking for a pure strategy Nash equilibrium, one of them is to play stop at every node. More generally, you can show that all Nash equilibria involve stopping at the first node. So there are some mixed strategy Nash equilibria in this game. So for instance, one mixed strategy Nash equilibrium would be player 1 stops at the first node, player 2 stops at the second node, and then players flip coins, say 1/2 everywhere else. Okay? That's a specification of strategies that would be a Nash equilibrium. Why would that be a Nash equilibrium? Well, player 1 is best responding. They're choosing to stop here and flip coins everywhere else, but given the strategy of player 2 to stop here, the coins are completely irrelevant in the sense that they'll never be reached. Player 2 choosing to stop here is a best response given that player 1 is stopping here, and player 2's coin flips down here never matter because the game is stopped by player 1 at the first node. So each player is playing a best response to the other players. So we have a prediction here that in all Nash equilibria, you'll have stop at the first node, and there are some more complicated equilibria where player 2 mixes even at the second node, but puts high enough probability on stop so that player 1 wants to stop at the first node. So there's a lot of Nash equilibria in this game. All of them involve stopping at the first node. Now, in terms of predictions, the Nash equilibria of this game give us some interesting predictions. They predict that the players are going to get very low payoffs. So the 4 and the 1 here are much worse than what they would like to do, which is somehow commit to passing along to get the higher payoff. So here they've got 320 in total. Here they're getting 5 in total. The difficulty is the incentives that they each face to be greedy and stop at each point along the way make it difficult to reach the 320 that lies at the end of the road here. So let's begin to take a look. So this game is very intriguing. It's one that gives us an idea that players' self-interested motives can lead to outcomes which are very bad compared to what the social optimum would be. And it's a richer game in some senses than A Prisoner's Dilemma, but nonetheless has the same kind of conclusion that we're getting a much worse outcome than players would like to see.